In this lecture, we're going to start looking at a couple new vector operations. So we've already seen how to scale vectors, how to add vectors. We've also looked at how to compute the length of vectors, how to write down vectors that go from one point to another. And today what we're going to do is look at the dot product. So we have these two vector operations that go hand in hand, dot product and cross product. We're only going to talk about the dot product in this lecture. Before I tell you how to compute the dot product of two vectors, let me just run through a few facts that are useful to keep in mind. The dot product is valid in any dimension. What I mean by that is that we can compute the dot product of any two vectors which are both in R2 or both in R3. Or, to write more generally, we could say Rn, where that would be like an n-tuple, so n-dimensional space. So as long as you grab any two vectors from the same space, you can compute their dot product. The result is a scalar, so the dot product of any two vectors is going to return you back a number. We will use dot product for the rest of the course, but one of the applications of it is it's going to give us a way to describe the physical concept of work. We'll return to this when we talk about the cross product. Again, these two go hand in hand, but some of the basic facts are different, so I wanted to kind of put that all up there together, and we'll revisit the distinctions between the dot product and the cross product before we move on to new topics. Okay, on this slide, let's say how to actually compute the dot product of any two vectors. And I've put a note over here that what we call dot product may also be called the inner product or a scalar product if you're looking in any other textbook. Dot product is really common in multivariable calculus, but you can also see this terminology. I've taken two vectors here, v and w, which are both in R3, but the formula we're going to write down is easily generalizable to other spaces. So suppose v is a vector whose components are v1, v2, and v3. So the x-coordinate of v is v1, the y-coordinate is v2, and the z-coordinate is v3. And let w be a vector whose components are w1, w2, and w3. So all of these coordinates are just scalar numbers. The dot product of v and w, which we write v dot w, and we never omit that dot symbol, is computed by multiplying their x-coordinates together. So that would be v1 times w1, plus multiply their y-coordinates together, plus multiply their z-coordinates together. You could write this as the sum from I equals 1 to I equals 3, vi wi, although it's not really necessary here. Okay, so it's a pretty simple calculation to do. Let's do a couple examples. The first one is in R3, just like the formula I wrote above, and then we'll do two vectors in R2, just to show you that it's pretty clear how to apply this definition to other dimensional spaces. So let's compute v dot w, where v is 1, 2, negative 1, and w is 3, 0, 1. So here v dot w would be 1 times 3, that's the product of their x-coordinates, plus 2 times 0, that's the product of their y-coordinates, plus negative 1 times 1, the product of their z-coordinates. So we get 3 plus 0 minus 1 is 2. Pretty simple. If we're working in two-dimensional space, like in the next example, we just pairwise multiply their x-coordinates and add to that the product of their y-coordinates. Okay, so here a dot b is going to be 3 times 2 plus 4 times negative 3. So let's see, that's 6 minus 12 is negative 6. If we had two vectors both living in R4, it's pretty clear what it would be. It would be v1, w1 plus v2, w2 plus v3, w3 plus v4, w4. Okay, before we go on to properties of the dot product, I just want to mention again that you never omit the dot symbol here. It's not like multiplication of numbers, where when you're a child, perhaps you used a certain symbol to indicate multiplication, and then later you just kind of would write VW, and that would mean V times W. Here we never omit the dot. Let's look at properties of the dot product. So suppose A, B, and C are vectors in Rn. So here I'm not going to specify the dimension of the space, and k is a scalar, so k is just a real number. A dot A, so any vector dotted with itself, returns you the length of that vector squared. I'll just write down a quick proof of that. All you have to do is just check that the formula works. So A dot A would be A1 squared, that would be like the x component of the vector A, plus A2 squared, plus dot dot dot, plus AN squared. And now that looks like the inside of the square root that we compute when we compute the length of a vector. So in particular, that would be the square root of A1 squared plus all the way through AN squared, this square root squared. But now what I'm squaring is exactly the square root we use when we compute the length of A. So this is the length of A squared. I mentioned this property here because sometimes it might be more convenient to use A dot A in a formula, and other times it might be more convenient to write the length of A squared. Or you might have a preference. You might prefer the one on the left and you see a formula written down with the length of A squared, so you want to be flexible. Okay, the second property says that A dot B is the same thing as B dot A. I won't write down a proof, but you can check why that would be the case. Right, so A1, B1 is the same number as B1, A1. So when we compute each of those terms that we add up to compute the dot product, it doesn't matter how we order the components of A versus the components of B. Okay, so number 2 tells us that the dot product is commutative. Property number 3 tells us that the dot product is distributive. So vector A dot the vector sum of B and C, so A dot B plus C, is the same thing as A dot B plus A dot C. So in the fourth property, I have vector A, which I would like to scale by k, and then dot with B. This property tells us that it doesn't matter when you actually do the scaling by k. So k times A dot B is the same thing as k times A dot B. So I could do A dot B first and then scale that by k, or if you wanted to, you could do A dot KB. And then the final property tells us that 0 dot A is always the scalar number 0. Keep in mind here the distinction between the notations. So on the left, that's the vector 0, and on the right, that's the scalar 0. The result of doing a dot product is always a scalar. It's never a vector. Okay, so if you look at properties 2 through 5, you might think that the dot product behaves exactly like regular multiplication. So regular multiplication between scalars is commutative, is distributive. And then in 4, if I treat A and B like scalars and k is a scalar, this tells us that multiplication is associative. And then we have a 0 element. But the dot product is not exactly the same. This is a special type of vector operation. So here's a property that's different between, say, regular scalar multiplication and the dot product of vectors. And that is, if A dot C equals B dot C, is A necessarily B? Where here perhaps we imagine that none of these are 0. In regular multiplication, that would be the case. So if xy equals zy and none of them are 0, then x equals y. That's called the cancellation law. Here it's not true. For example, have A be the vector 1, 0, the vector I if you want, and C is the vector 1, 1. That product gives you the same thing as j, so 0, 1, dot 1, 1. So that's a counterexample to the cancellation law. So while the dot product is not too difficult to compute and it has a lot of the same properties that we might expect from a type of product, it's a special operation for vectors. Okay, now why do we even have this dot product? Let's look at the geometric meaning of the dot product. So the dot product gives us a special piece of information about the two vectors that we dot, and let's see what that is. So here's the major piece of information that the dot product tells us about the vectors A and B. So let A and B be any two vectors in the same dimensional space. Here it looks like R2, but it doesn't have to be R2. Let theta be the smaller of the two angles between them. So here I have this angle and I have this angle. So theta is going to be the smaller one. The dot product of A and B is the length of A times the length of B times cosine of theta. This is a really useful piece of information. So in particular, if we're given A and B, it's not too hard to compute their dot product. It's not too hard to compute their lengths. But if I just told you two random vectors, it would be really hard to calculate exactly the angle between them without this formula. We don't do too many proofs in this class, but I do like this proof, so I'm going to take you through it. So what I'm going to do is take this configuration I have here in the top right and turn it into a triangle by adding in a third side opposite the angle theta. Let's call this side C. And then through vector addition, notice A plus C equals B. In other words, C is the same thing as B minus A. Okay, we have a triangle here. It's not a right triangle necessarily, but we do have three side descriptions, A, B, and C, and we have an angle. With this, we could try to apply the law of sines. That doesn't seem very relevant here because we actually have cosine of an angle, so instead we're going to use the law of cosines. So the law of cosines says that the length of this side, which to start out I'll use the letter C and then we'll switch to B minus A. So the length of that side squared is equal to the length of the other two sides, so the length of A squared plus the length of B squared, minus twice the product of their lengths, so twice times the length of A times the length of B, times cosine of that angle opposite C. So that's the angle that we're interested in. Let me take this left-hand side here and I'm going to replace it with B minus A, and then we're going to use the first property that we saw back here. We have magnitudes of vectors squared. We're going to replace them with dot products. So on the left-hand side, we have the length of C squared. But through vector arithmetic, we know that that's the same thing as the length of B minus A squared. And then through property 1, we know that that's actually the vector B minus A dotted with itself. Now through property 3, we know that vector dot products are distributive. So we could write this actually as B dot B minus B dot A minus A dot B plus A dot A. Now on B dot B and A dot A, we'll use property 1 again. And then for the middle terms, we'll use the fact that the dot product is commutative. So B dot A is the same thing as A dot B. So I can simplify this to the length of B squared minus twice A dot B plus the length of A squared. That's all now for the left-hand side. So we took the left-hand side of the starting equation and we can replace it with this new expression. So let me write that all out, then we'll cancel out what they have in common and we'll be left with the theorem that we have at the top. So let's see, I'm just going to reorder the terms here. On the left, we have the length of A squared plus the length of B squared minus twice A dot B equals our original right-hand side written exactly as I wrote it on the first line. So the length of A squared plus the length of B squared minus twice the product of their lengths, so the length of A times the length of B times cosine of the angle between them. Now we can cancel out the length of A squared, the length of B squared from both sides because we have them in common. So then we're left with negative 2 A dot B equals negative 2 times the length of A times the length of B times cosine of the angle between them. Now we divide both sides by negative 2, and we get the formula that we're looking for. So A dot B equals the length of A times the length of B times cosine of the angle between them. Okay, let's talk about how useful that formula is. So first of all, as I already mentioned, if you're given A and B, say I just give you two vectors, you can compute their dot product, you can compute their lengths without too much difficulty. But how would you compute the angle between them without this formula? You try to graph them and put down a protractor or something. So One of the major consequences of this theorem is it tells us that the cosine of the angle between them is A dot B divided by the length of A times the length of B. Of course, this formula only makes sense if neither vector is 0, as otherwise we would be dividing by 0, and that's not something we want to do. Now this formula is perfectly valid for angles that we can graph. So we can graph angles very easily in R2. With a little bit of difficulty, we can try to plot vectors in R3 and see the angle between them. But this formula here actually gives us a way to define the angle even in spaces that we can't see. So we can't draw a picture of R4. But now we can say how you could compute an angle in R4 even if you can't graph the vectors. Okay, let's talk about some famous angles here. So what if the angle between them is 0? And then something that's really useful to know, what if the angle between them is pi over 2? In other words, what if it's 90 degrees? Okay, so what happens if the angle between them is 0? Well, in that case, cosine of theta is cosine of 0, which is 1. You should know that, by the way. So if you're a little bit rusty on the unit circle, make sure you have that handy and kind of revisit the famous angles, the famous values of sine and cosine. Well, in this case, if the angle between them is 0, that means that A and B are pointing in the exact same direction. So perhaps this is A and this is B. They are parallel and pointing the same direction. In that case, our formula reduces significantly to just A dot B equals the length of A times the length of B. Probably more interestingly, what if theta is pi over 2? Well, in this case, cosine of theta is cosine of pi over 2, which is 0. In other words, A and B are perpendicular. And then when we plug cosine pi over 2 into the formula, we see that A dot B must be 0. And that's a really key result. In fact, it's going to lead to our theorem at the bottom. So this is a key notion here. Two non-zero vectors A and B are orthogonal. That's the word we use most often to say perpendicular, so 90-degree angle between them, if and only if their dot product is 0. We can say that A is perpendicular to B if and only if A dot B is 0. Here I've used the phrase if and only if, and that is actually what this symbol that I drew down here means, this kind of double arrow symbol. If and only if means that both sides must either be simultaneously true or simultaneously false. So if A is perpendicular to B, then it must be the case that A dot B equals 0. And if A dot B equals 0, then A must be perpendicular to B. These go hand in hand. I said non-zero vectors here, but if one of them is 0, we typically think of the 0 vector as by default perpendicular to everything. So this is of course more interesting when we're looking at non-zero vectors like I've sketched up above. Let's finish with a couple examples. So here I've given you two vectors in R4, four-dimensional space. We can't try to graph it. A is the vector 1, 1, 1, 7, and B is the vector 2, 0, 0, 0. We want to find the angle between A and B. Now I can't try to graph these. I don't have a four-dimensional protractor handy, but I do have this theorem about the dot product. Okay, so what we know is that cosine of the angle between them is going to be A dot B divided by the length of A times the length of B. Okay, so let's compute the numerator. A dot B. It's not too bad of a dot product since there are so many zeros in B. We're going to have 1 times 2 plus 1 times 0 plus 1 times 0 plus 7 times 0. Of course, you don't have to write all that out. You could just write 2. Now, what is the length of A? That's going to be the square root of 1 squared plus 1 squared plus 1 squared plus 7 squared. So let's see, that's 3 plus 49, so that's square root of 52. The length of B is really easy. That's just 2. Okay, so we can write down now that cosine of theta is A dot B, which is 2, divided by 2 times the square root of 52. 2's can cancel, so that's going to be 1 over the square root of 52. Okay, so what that tells me is that theta is going to be the arc cosine of 1 over the square root of 52, which is approximately 1.43 radians, or if you prefer, that's approximately 82.03 degrees. So that's an example of how to use the dot product to compute the angle between two vectors. Our final example for this lecture, I haven't given myself very much room down here at the bottom of this slide, but we want to find a vector which is orthogonal to the vector 1, 7, negative 2. There's not a unique solution here. I'll show you in a minute that there are actually infinitely many solutions. But the key idea is to find a vector whose dot product with 1, 7, negative 2 is 0. Now you could write down an equation with 3 unknowns here, but let's make our lives easy. What I recommend doing is taking 2 of the coordinates, switching them and negating 1, and then zeroing out the third coordinate. It's going to be easier to understand once I write it down. So for example, I could write negative 7, 1, 0. By zeroing out the third coordinate, that means I don't have to worry about negative 2 at all, because when I compute the dot product, I'm going to have 0 times whatever this is. And then by switching the other 2 components and negating one of them, I'm ensuring that when I compute the dot product, they're going to cancel out. So we'll have 1 times negative 7 plus 7 times 1, that gives us 0 plus 0. Of course, other things would work as well. I could zero out the y coordinate and write about 2, 0, 1. That would work. We'd have 2 plus 0 minus 2. Could zero out the x coordinate and write 0, 2, 7. Same story, that will also work. But actually, these are just 3 special ways to answer this question where I've done this kind of algorithmic approach, giving myself an easy dot product. There are actually infinitely many vectors that would work, and let me show you a picture. Okay, so this vector sticking out of the plane is the vector 1, 7, negative 2. Then this one on the bottom is the vector negative 7, 1, 0. This one in the middle is sticking kind of straight up. This is the vector 0, 2, 7 that we've already written down. And that leaves us over here on the left with the vector 2, 0, 1. So we found these 3 particular vectors when we answered that question a minute ago. But notice here that actually an entire plane is perpendicular to the given vector 1, 7, negative 2. So as long as I pick any vector which is on this plane, it's going to be orthogonal to this given vector. So we can think of this vector as orthogonal to the plane. It's kind of like if you're sitting at a desk and you have a pencil with you. Hold your pencil straight up over the desk so that it's pointing out of the desk. And then any vector that lives on your desk is going to be perpendicular to the pencil. So if you struggle to see this 3-dimensional picture on this 2-dimensional screen that you might be looking at, try to recreate this in your own space. We're going to use this fact a lot actually. So when we're working in R3, we think of a vector as perpendicular to an entire plane. That finishes this lecture on the dot product. Thank you for your attention.